Andy, for the introduction, but I just wanted to say it's a great honor to have been invited to present this lecture today. So I'd like to thank the conference chairs, and I'd like to thank the ESIS president for the invitation. I'm going to be talking about some of the work that I've been doing in fracture of structural adhesive joints. I've called it achievements and challenges, but of course this involves the achievements of a large group of people. So this this figure hopefully gives the explanation. So the grumpy looking person on the right is me. I'm sat here behind the computer whilst you're all enjoying the wonderful climate and surrounds of Funchal, Madeira. I tested positive before coming, before the flight, and this is the first time I'd had COVID, so it was a great disappointment to have got it just before this conference. Looking at these tests, which I hope you can see, in research you have to have the eye of faith. And looking over the last 7 days, we see at the bottom right, I'm thinking that the positive line is just looking a little bit thinner. So maybe I'll be negative soon. But anyway, that's probably my my eye of faith in this area. Andy mentioned my connection with ESIS TC4, and also the fact I've been on the executive committee of ESIS for the last 2 excos. Which has been a great privilege. But I think one of the things that it's given me the opportunity to see is the great work that the technical committees do within ESIS. Many of the technical committees are fantastic centers of activity and are pushing the science and the application forward in many exciting areas. In terms of TC4, which I co-chair with Andy Brunner, TC4 is the 4th oldest of the TCs, and in fact it was conceived at ECF5 in Lisbon, Portugal in 1984, and it held its first meeting in October 1985. So this year TC4 is going to be 37 years old. The original chairs were Gordon Williams and Henning Kausch, shown photographed here. And on Hennig's retirement, Andrea Pavan took over and co-chaired with Gordon Williams until Andreas and myself took over in 2017. Sadly, Hennig passed away in 2019. I just want to give a quick plug for the areas of activity of TC4. Hopefully TC4 members are influential, but just to say that the areas of activity have really been in fracture mechanics test method development for polymers, for composites, and for adhesive joints, and that includes peel. So traditionally and historically it started with K, and K for polymers and G for composites, and that was in mode 1 and then mode 2 and mixed mode, and more recently J. And also areas of activity have been trying to understand the resistance to fatigue loading, to high-speed impact. There's been lots of work on high rate applied to both polymers and also composite materials, and also environmental effects. And at the moment we have a particular focus on new polymeric-based materials. They could be laminates or composites, and also in terms of non-conventional test methods. The committee have been interested in methods like scratch testing and also cutting, where toughness values can be backed out of the test. And of course, this gives the opportunity to test various materials which are otherwise very difficult to test from more conventional fracture mechanics methods. I'll just give a quick plug for Andy and the session on Friday morning, topic TC4, fracture testing of novel and advanced polymer-based materials with new or unconventional methods. And my last slide here is just to plug our conference. So TC4 have had a conference on a 3-year cycle. Since the first meeting in Sardinia in 1993, it's been on a 3-year rotational cycle since 1999 up to the present day, with a small interruption for COVID where we went virtual in 2020-2021. We always meet in Switzerland, in the mountain village of Lady Aberay, where you can see the scenery is perfect. The cuisine is also extremely good. For the 2023 conference, we have an abstract call out currently with a date for the 30th of December. So anyone is interested in this type of material, please do feel free to pop in an abstract, and we can meet. So coming to the presentation, I want to talk briefly about why we use adhesives, and then to look at some of the issues that we run into when we're fracture testing of structural adhesive joints. And I'm going to limit myself to mode 1 and mode 2. But of course, mixed mode problems are also prevalent. I won't be discussing mixed mode today, and I'll end with some challenges. So very quickly, adhesives in action, and we can see here that adhesives are used in airspace and aircraft to a large extent. In fact, adhesives are a very efficient joining solution because you don't have to introduce holes to the structure. There's no need to drill holes for rivets if you're adhesively bonding. So the stresses are nicely uniformly distributed across the two mating surfaces. And adhesives are very useful and successful in joining different materials. So they're a good multi-material joining solution. The slight disappointment with aircraft is, of course, that due to the fact that there's no current successful test for detecting kissing bonds in adhesives, in adhesive joints, then adhesives tend to be limited to secondary structures in aircraft. Obviously, that's an active research area. But looking at the structure, you can see some of the places where adhesives are used. So structural film adhesives, which are used widely in aerospace, are used here along the wing sections for spoilers. They're used in the vertical tailplane, horizontal tailplane. So many applications structurally around the aircraft, adhesives and toughened adhesives are used. Moving on to the automotive industry. So the automotive industry is also another large user of adhesives. And several structural epoxy adhesives have been developed which have excellent impact resistance. You can see in the image on the top, hopefully you can see the orange seams holding parts of that aluminium structure together, which is connected to, in that case, a carbon fiber composite part. But you can see there that the adhesive is positioned and designed to resist impact loading, such that in the event of an impact, then the structure will progressively crumple. The adhesive will hold together, ensuring that the metalwork deforms, absorbs energy, and absorbs the crash energy of the vehicle collision. Now, also advantages of adhesives in this sort of application are that compared to welding, they would stiffen the structure, and they'd also improve the noise, vibration, and harshness characteristics. They're very good at damping vibrations. So adhesives are very widely used in the automotive industry. But of course, to be able to use adhesives with confidence, we need a fracture mechanics framework. So we need to be able to take the different types of loading that should form in a structure, and in the classic fracture mechanics way, we separate those out into modes 1, 2, and 3. And of course, we can have mode mixes, combinations of those, and we use various different methods to determine these fracture parameters, G1C, 2C, and JC, for example. So they're the ones I'm going to be talking about in the talk this morning. Of course, they would then feed into performance models so that we could understand better how the structure behaves, and, for example, for how long the structure may last. So that, if you like, the service lifetime would also require these parameters. So moving now to the application of fracture mechanics to adhesive joints, then certainly in terms of the mode 1 tensile opening methods, following on the pioneering work of Griffith and Irwin, Rippling, Mostovoy, Patrick, and Crosley in the 1960s developed two very successful structural adhesive test geometries, and they were the DCB and the TDCB. So they were very popular, and based upon those two geometries, an ASTM standard was published, which was D3433. And the analysis employed was based upon shear-corrected beam theory, where the compliance took into account the contributions of bending and shear, and then, of course, the compliance is differentiated into the Irwin-Keyes equation, and the equation for G1C could be fitted in this way. Now, a rather nice design was to recognize the term in blue brackets here could be held a constant to simplify the analysis. And that could be achieved, for example, by height tapering the beam, which led to the tapered double cantilever beam that we saw on the last slide. And the tapered double cantilever beam will be designed with a constant value of M. Of course, the actual geometry will vary as M changes, but typically you can use a value of M to hold the rate of change of compliance constant. And of course, there are great advantages for doing that. So when we revisited this very popular ASTM test method, we looked at two issues in this test. The first issue was that the contoured part of the beam, that part which is tapered, such that M is held constant, doesn't extend for the whole length of the beam, but is discontinuous. And you can see that leads to a compliance error, if you like, in the early part of the beam. So the straight flat part of the beam, which we say here extends x0 from the load line, basically has a different compliance characteristic to the rest of the beam. So that needed to be recognized. And you can see that if one extrapolates the linear changing compliance to zero compliance, you actually get an intercept at some portion of the untapered region x0. It turns out to be 2/3 of the length. But that's, if you like, a compliance error that you run into if you assume the beam profiles down to zero crack length. And second thing that needed to be looked at was the root rotation. So the original shear-corrected beam theory didn't take the root rotation term into account, which has important consequences. So if one looks at the compliance against the crack length using, for example, the original simple beam theory, then there was both an error in slope and an error in intercept based upon the original analysis. And when we were developing the ISO standard for the mode 1, we took those two terms into account, and we ran a series of round robins within the ESIS TC4 group to look at that effect and to to work out the accuracy and the reproducibility. But that solution for the tapered double cantilever beam was successful. So in the ISO we were developing, implemented corrected beam theory, which included root rotation term and corrections for large beam deflection and end block stiffening, and also the corrections that I just mentioned to the tapered double cantilever beam. And we implemented a simple shear corrected beam theory, a corrected beam theory, and an experimental compliance method. So in terms of fracture resistance, those methods and determination of G via the three methods work well. And one thing that we wanted to explore additionally was the use of an effective crack length approach. So in addition to the three methods for reducing the corrected beam theory for CBTE, and the idea of that is that the use of effective crack lengths can negate the need to measure crack length. So there are situations a little bit like with the tapered double cantilever beam where you can negate the need to measure crack length. So you can if you're using effective crack length approaches. And various groups have implemented different versions of CBTE method. And I'll return to those in a little while because obviously they're also can be used in mode 2. But this is a fracture test specimen. You can see the adhesive on the right, and this is a structural film adhesive. So this is the sort of adhesive that may well have been used in an aircraft application. And you can see that we generate an R curve. The methods are in broad agreement in this case, and you can see that we've got a fully cohesive fracture surface. So there's no aspects of interfacial failure in what we're looking at. Now, great progress has been made in toughening adhesives, and many groups around the world have implemented different and toughening rubber, core shells, small core shells, nanoparticles, and combinations thereof. And very impressive results have been achieved, and large increases in toughness have been achieved by different groups. So there's a testing challenge here, and that's the validity of them when the materials become very tough. So to what extent are the methods that I've talked about valid when adhesives become extremely tough and or ductile? DIC, so digital image correlation techniques, have become very popular in the last 10 years. So many groups are using DIC. So not only can you look at the strain fields, but you can use DIC to inspect displacements and rotations on a system. So it's a very versatile technique and one that we've used quite widely. And of course, what you can do with, for example, a double cantilever beam with a bonded adhesive layer is you can set up inspection points on the surface of the specimen. And then you can take high resolution digital images, and then you can process those with a DIC analysis software to take out the displacement points. And one of the advantages of this technique, of course, is that it is a technique which can be automated. And particularly thinking of mode 2, where it is very difficult to measure crack length, but often in mode 1 we have significant issues measuring crack lengths as well. So techniques which have the potential to automate crack length measurement are very desirable. Another thing that can be done, so several groups have used these sort of techniques where you don't measure displacements and rotations directly on the surface by DIC, but you use, for example, an inclinometer device. So in the image on the bottom left, you can see an inclinometer is attached to the lower arm of a DCB specimen here, with the idea to measure the rotations. So there are techniques where we can measure the displacements, and these displacements can be measured both behind and in front of the crack tip, and also the rotation angles. And this is a powerful approach because we can then achieve several things simultaneously. So one of the things that we looked at was, in fact, looking at, from the DIC data, the displacement profiles ahead of the crack tip. And this enables us to do this with quite a high degree of accuracy using DIC. But what we're able to do here is we're able to measure the displacement profile ahead of the macroscopic crack tip. And that's shown by the red line in the data. And of course, one thinks about the traction separation law additionally. And one of the things that we wanted to do is to define as accurately as we can the effective crack length. As I mentioned earlier, the effective crack lengths have an advantage. And if we can come up with routines for automating their measurement, then we can implement those effectively in the analysis solutions. So if we're looking at a diagram here, you can see that the region O to A is typically the region where we are representative of damage ahead of the crack tip. And the region A to B is the elastic tension region. And then for the sort of materials that we're looking at, bonded joints, we then have a compressive region. What we can then determine is, well, what is the correct crack length to be using in our analysis. So typically one would think that the effective crack length should be the value A0 plus the length of the fracture process zone, LFPZ, taking you to point A. But of course, there is a problem with that, and that's that at point A, or certainly at point B, then at point B you would have a zero displacement, but you would not have a zero slope to the displacement. And we've looked at different ways of defining this effective crack length, and the best scheme that we've devised is to take the position C, where the slope of the displacement is zero, despite the displacement not being zero. So we're defining an effective crack length here via a delta A term, which takes us to point O to C. And the rationale for doing that is that the slope of the displacement is much more important to the compliance. So the compliance has a higher sensitivity to that than it does the displacement. So with the DIC, we can track out the values of effective crack length, which we can feed into the beam theory. We can track out rotational angles, either using the DIC method or using inclinometers. That's been done by several other groups. And then we can measure traction separation laws. And we can do that simultaneously whilst measuring J for the adhesive. So this is some data that we had for one particular adhesive. This was an epoxy paste adhesive, where we've used a digital image correlation, and we've developed the relationship between J and the displacement delta, in this case, the opening displacement term, and using different schemes for controlling that relationship, then we can determine the traction separation law. So we can think in this case of the direct differentiation of the stress displacement function as being like the experimental value, and then we can apply different techniques to simplify that. So this is quite an interesting approach. I know many groups are using DIC and extracting traction separation laws and J simultaneously in this way. So in terms of what it means for the adhesive, then we can compare, of course, G values via different techniques: simple beam theory, corrected beam theory, and different effective crack length approaches. And we can do that for different adhesives. So on the left, we're looking at a tough adhesive. This is a Seeker Power 497. So this is an automotive adhesive, highly toughened and crash resistant. And we can see in this case that the methods are giving us pretty good agreement. The plateau value of J and G via the different techniques are quite closely correlated. However, for the more ductile adhesives, you can see this is where you begin to have differences, and it begins to be more challenging for LEFM methods, even with the corrected beam theory and the effective crack length approach to give the agreement with the J values. So I want to end by saying a few things about Mode 2, which is currently a big work activity area for ESIS TC4 and for myself at Imperial. We know there are different ways of introducing Mode 2, and this is one of the challenges that whilst there was general agreement with how to perform a Mode 1 experiment, there are widely different ways of introducing Mode 2 to a specimen, from 3-point flexure to 4-point flexure to tapered end-notch flexure to, for example, an end-loaded shear joint. Different workers have used different ways of doing this, and at Imperial and in the ESIS TC4 committee, we've used the end-loaded split. This is a specimen which is clamped as a cantilever, and the clamp is based upon a linear bearing trolley, and then the specimen is bent, and that introduces a state of pure shear at the crack tip. And of course, what then happens? Well, of course, as you deflect the beam, you impose the shear stresses at the crack tip. And if the adhesive is a toughened, highly toughened adhesive, as are many of the adhesives that are of interest, then we have an extensive fracture process zone develops. And this can be really quite extensive in Mode 2. In addition to plasticity, for example, one can also see a micro-cracked region, depending upon the precise details of the adhesive, the balance between the toughness and the ductility. You can get a micro-cracked region. This obviously poses a number of challenges, one of which is a fundamental challenge to say, is this genuinely Mode 2 fracture? So Kevin O'Brien from NASA Langley wrote a very nice article many years ago saying, is this process shear failure or shear myth? And he was referring there specifically to composites, but of course the same can be argued for adhesive joints. So locally, of course, what's happening here is more akin to Mode 1. Globally, it's a Mode 2 fracture phenomena. And of course, there is a large energy dissipation associated with it. So what one school of thought says, don't go here, measure Mode 1, and that's all designers need to know. And another school of thought, which is closer, I think, to where I stand, is that this is a real phenomena, and the combined response of all of these Mode 1 micro cracks, if you like, leads to additional energy dissipation, which we need to know about. If we're interested in conservative designs, then we want to be able to take this into account and measure it reliably. So, of course, one can go through a similar sort of procedure. One can apply simple beam theory and experimental compliance methods. One can develop effective crack length approaches. So all of these things can be done a little bit analogous to the mode 1, and one can look at how they improve the compliance to the crack length variability, the relation. And one thing we can see here is that because we have a clamp in the experiment, we do have to calibrate that clamp out. But indeed, we can get a theoretical compliance which looks pretty close to the experimentally measured one. But what I would say about this is the method, and certainly the G analysis with effective crack length approach, I think has passed the limits of its validity. So one can of course inspect this by measuring J, and we've been doing this, and I know labs in various universities have been using techniques to measure J. And what we do find is that when we do this for this particular adhesive, then the J values are lower. So it would seem that if one is trying to develop a standard for mode 2, then if one wants it to be able to cover an incomplete toughness range, then most likely it has to be a standard involving J. Whereas if one is content only to go to an intermediate value of toughness, then G with effective crack lengths would be sufficient. But this is clearly an activity area that we're working on. I know different groups are working on around Europe and across the world. So I want to end just with some thought of challenges that we face. Certainly the challenges with adhesives and characterizing their fracture resistance becomes more challenging as they become tougher. And mode 2 does pose us additional challenges, not only in how to test and to measure, but also fundamentally whether this is fundamentally the correct approach to be taking, whether mode 2 really means anything. As I said, I'm in the camp where I think we should measure it, and we should be aware of the energy dissipation so that we can use it in design. But I'm fully aware of many counter views on that. And of course, we're interested in characterizing under different types of loading. So current big areas are dynamic fatigue, impact, different environments, of course, hot and cold, and wet and corrosive. They all remain challenging. So I just want to end, please join us in TC4 to work on these exciting challenges. And Andy, I'll hold it at that. Thank you very much.
Thank you very much, Bamber. I think